me welcome you to this fourth lecture on our course on reinforcement learning. And today we are going to continue along the path of discussing various applications, how we formulate problems, different important types of different problems. And we're going to discuss POMDP, partial observation, Markovian decision problems, systems with changing parameters, and the time-honored subject of adaptive control, and then model predictive control, which is the dominant current methodology in control theory, at least as far as research is concerned. So here's the outline. We're going to review some material from the previous lectures on how we formulate problems, and then focus on partial state observation problems, then discuss adaptive control, which relates to problems with changing parameters. The model changes on us as we control the system. Then model predictive control. And this lecture, we'll round out the four-lecture introduction to the course. Remember, the first four lectures in this course are foundational. And they're sort of summary lectures, summarizing the methodology without going too far into the details. Starting from the next lecture, we're going to selectively focus on particular methods and problems. And at the end of this lecture, we're going to summarize what we have done, where we're going, and a lot of the things that we have not covered. Reinforcement learning nowadays is a vast field. And we are focusing on this course on methods that I think are self-consistent, consistent with each other, and also have the most promise, in my opinion, for being useful both in the present and in the future. However, there's a lot of stuff out there that we will not cover, either because I think it's not relevant, or it's not very good, or because we just don't have enough time. So we're going to have a list of that, and then you can go off to the literature and read details if you're interested. So, review problem formulation. How would we formulate practical problems as dynamic programming problems? And I mentioned an informal recipe. That's my recipe. That's how I go about formulating dynamic programming problems. First, define the controls. And that's generally easy. I mean, given a practical problem, the things that are under your control, the things that you can choose, are the natural candidates for control. Then the next thing that you have to decide is how do you discretize the problem or a finite or infinite horizon? The stages, define the stages of control. And basically, the standard recipe for this is to look at when information becomes available. When new information becomes available, typically that's when you have to apply controls. But this is not universally true, and sometimes the same problem can be formulated with a finite horizon and an infinite horizon, or with a different number of stages. It's something that you need to look into. Now, the hardest part is to define the states. What are the states? And part of the problem is that there are many different quantities that you can define as state, and all of those can be legitimate. So the recipe here is this. We define as state, xk, something that summarizes the past for the purposes of future optimization. In other words, if you are at time k and you know this xk, then all the past information that you may have received, previous values of previous states, other things, they're irrelevant. In other words, you can do just as well by ignoring this other information and focus on this xk. So xk is related to, the proper choice of xk is related to the concept of sufficient information. Sufficient information for doing as best as you can for your future optimization. And the rationale is this, for this is evident. The controller applies action that depends on the state. That's the feedback that we receive in dynamic programming. Therefore, the state should subsume all the information that can be useful for decision control. Now, okay, so that's a simplified recipe, but it's deceptively simple. The ultimate test is to write down a correct dynamic programming algorithm. That means write down the system equation, how the state evolves, make sure that that makes sense, write down the cost per stage properly, include the constraints, figure out what the constraints are, the probabilistic descriptions, the fact that the disturbance at time k should not depend on previous disturbances. There are no correlations, should depend only on the current state on the control. All of these are important, and you should pay attention to the math, I think, because my experience with teaching dynamic programming goes back 50 years. And I have seen students and their background evolve over time and their approaches. And in the beginning, okay, in any implementation, there's the mathematical formulation, and then there's the coding, okay? In the early days, there was no coding. The classes, dynamic programming classes, did not have coding. Coding started getting into classes maybe in the 90s or so, okay? I personally have never taught a course that involved coding except for term papers, and that only happened in the last 20 years or so. Now, the situation has changed because the background of students has changed. You get the, and also the equipment that you have is so much more powerful, the computing equipment. And you get trained in coding and you do a lot of work in coding. And there's a certain temptation here because dynamic programming is a very simple methodology. You get the drift of it right away. There's this principle of optimality. Optimize at the present, the next stage, plus the future. That's easy to understand. And then there's a tendency to go straight into coding and skip the mathematical formulation or the detailed mathematical formulation part. Now that may not work well at all. The reason is the following. People go into coding because they think that if they make a mistake, the computer will correct it, okay? Either your problem will crash or the numbers that are going to come out are going to be nonsensical, and you're going to figure out that you have to do something about it and correct your program, correct your rationale. On the other hand, in dynamic programming, it's very easy to write a code that doesn't crash, that gives numbers that look reasonable, but in fact make no sense. They're wrong numbers. It's very easy to, and it's very difficult to figure out when this happens. So it's important to pay attention to a proper mathematical formulation, that all the assumptions are there and that you can write a correct mathematical algorithm. Okay, so that's my 2 cents from 50 years experience, because I've seen a lot of students in recent years that they just write incorrect dynamic programming algorithms, and then they can't even figure out why this is wrong, okay? Because they haven't dealt very closely with the details of what the methodology is supposed to be doing. Okay, so now I mentioned that figuring out what the state should be is the harder part, and part of the reason is that there may be multiple useful ways to define a valid state. And an important example of this is POMDP, partial observation Markovian decision problems. So let me discuss what these are. They're a very important class of problems, arises very often in practice. And our basic assumption in dynamic programming has been that we observe xk, some xk that makes sense as state, right? We observe it exactly. On the other hand, in many problems, we can't observe it exactly. And instead, we obtain some measurement, zk, that's related to the state, but does not give you exactly the state. So xk is not exactly observable, and it violates the assumptions of the basic dynamic programming formulation. We need to redefine the state. This xk does not make some sense on an intuitive basis, but it may not give you a correct mathematical dynamic programming algorithm. So based on this idea of defining xk as the state as something that summarizes the past for the purpose of future optimization, one possibility is to look at what we have at time k, which is all the information, what we can call information state. And that information state includes all the measurements that we have received up to time k, and all the controls that we have applied up to time k. And I mean, that's the ultimate information, all the information. So it should be an appropriate state to use. So it can serve a state. However, there are other possibilities. The so-called belief state in POMDP problems, which is really a state that is a probability distribution over the xk's. So let's discuss this in the next slide. Are there any questions here? Yes.
When you say the stages, do you mean time steps?
Time steps, n, the length of the horizon. Oh, wait a minute. That's one thing, but the stages is, okay, we say xk plus 1 equals f of xk and so on. What is k? What does this represent? Practically speaking, is it every 5 minutes? Is it every day, every week? Okay, so there's a choice to be made there, and there are trade-offs involved. Okay, so an example, let's focus on partial state information problems, and let's introduce those with an example. I used to give this problem as a homework problem for many years, and it's actually a homework problem in your textbook, although we don't assign it. We will not assign it this year. It has to do with a parking line involving M parking spaces and a driver that goes up and down the line trying to find a parking space to park and moves one spot at each time step in either direction. Either it goes to the right or he goes to the left, and can go further steps to the left, can come back to the right, and so on, looking for a place to park. Now, if he decides to park at spot M, assuming the spot is free, right? Then there's a cost CM. But the cost, but the spot may also be occupied. And what the driver does is observes just one spot, the spot that he's currently at, okay? He cannot observe 2 steps ahead or 1 step behind, only the spot that he's at, and looks at the spot and can determine whether it's free or not. And if it's free, makes a decision to park or not to park and go to the left or to the right. Now, the thing is that once you observe a spot, the status of that spot may change over time. In other words, if this spot turns out to be occupied, 2 steps later, it may become free. And if a spot is free, it may become occupied sometime later, according to some probability. There's a Markov chain involved here. A spot that is free will become occupied with a probability, let's say, 20% in the next step, okay? And reversely. We assume that we know these probabilities. So that gives us the knowledge of the probabilistic description of the problem. And given our observations, what are our observations? As we go forward or backward, we observe the status of these parking spots. These are observations, right? And the probability distribution of occupancy of the entire line is something that can be calculated and can be updated over time, right? Spots that have been free in the past may become occupied and so on, and you can calculate this probability distribution. Of course, if this M is large, there's a huge probability distribution, and you have to keep track of that, but the formulas are easy to write down and there are equations for those, estimator equations. So the free taking status of the source is estimated in a probabilistic sense based on the observations. And the observations are the free or taken status of the spots visited whenever they're visited. So what should the state be? What is the information state here? Can someone tell me? That's our first candidate for state, a legitimate state, the entire information vector up to the present time, the entire history of observations up to the present time, what we have seen by going up and down the line, right? So it's possible to write a dynamic programming algorithm with this information state, and it's a legitimate algorithm. On the other hand, it may not be the best because to begin with, it expands over time, right? We add more and more observations, it becomes difficult to manage. And computationally also, it's difficult to deal with. Now, there's another candidate here, which we call the belief state, which is the probability distribution of the current status of the parking line. In other words, the set of conditional probabilities of free taking status of all the spots. These probabilities here, that's the belief state. How will we think of the parking lot, and we can, with this belief state, we can figure out which parts may have free spots more than others and so on. This is an evolving probability distribution of the state of the parking lot. So now there's an advantage to this belief state. It doesn't expand over time. This dimension does not expand over time. And on the other hand, there's also a disadvantage because this information vector can have a finite number of values, right? There's only free taking status, discrete variable over the current time. Whereas these are continuous variables. Probabilities are continuous variables. That means that we have to formulate a dynamic programming problem over a continuous space, which has difficulties of its own. Okay, so that's the example. A new state is some kind of probability distribution over something that looks like it's appropriate, and also this probability distribution encodes all the information that is available up to the present time. And here's now the general formulation. The first thing is this belief estimator. This belief estimator is some kind of filter, Kalman filter, particle filter. There are several of those available in the literature, and you may have heard of them. And this belief estimator becomes the state of a new system, the belief state system. We denote here by BK, this belief state. It's a probability distribution, and it evolves over time according to some equation given by this estimator. So BK plus 1 depends on BK, the control that we apply, which can affect the quality of the estimation of the belief state, and also the observation that you get, right? The observation that you get is going to come in to affect the belief state. So we have this system here, which looks like a discrete time dynamic system. Its state is this BK now, a different state than before. And it's a probabilistic estimate of the unknown or state, what you would like to be state. So the controller takes in this belief state from the estimator, applies control that's a function of the belief state, and together with the observation that comes in at each step, it generates stochastically the new belief state. So it's a system pretty much like the ones we have been dealing with, except that this estimator becomes the FK type of system that we had before. So we introduce this belief estimator. This is the next belief state given the current belief state BK, given that UK is applied, and observation ZK plus 1 is received. And this may be described by equations, such as in Kalman filtering, if you have encountered this type of estimator before. It's a very common. Or by simulation. There's something called a particle filter, which is a simulation. There's a computer. In other words, this estimator becomes available through a computer model, not a mathematical model, but a computer model, which estimates this belief state, provides this belief state. So that's our system, our control. Our disturbance now is this observation zk plus 1 in the system, what we called earlier disturbance. And we can write a dynamic programming algorithm based on this new formulation. Now, the state is the belief state. So J star is going to be a function of BK, right? And the next state, BK plus 1, is going to come in here, right? J star K plus 1. And now this is expected value over the disturbance, the uncertain quantity. And it's conditional expected value given BK and given UK. Okay. So J star of BK denotes the optimal cost to go, starting from belief state BK at time K. UK, capital UK is this control constraint. And the cost function here is expected cost. And I have written it here more compactly as G hat. By definition, it's the expected value of the original cost that we had, formulated in terms of XK, UK, and WK, conditioned on BK, the current belief state, and conditioned on the control that we apply. So this expected value can be computed because the distribution of XK and UK is determined by BK and also the distribution of WK. There's a lot of formulas here involved, but intuitively this makes sense. So let's leave it at that. So how does this algorithm work? Well, it works backwards. Given the optimal cost to go at time K plus 1, we do this minimization. The expected value, ZK plus 1 is we take the expectation of that, so it doesn't come into the minimization. This expression here, given J star K plus 1, depends on BK and UK. This also depends on BK and UK. Minimize over UK gives us a function of BK, right? So just checking the variables here, this algorithm makes sense and can be executed. Obviously, this is an extremely difficult algorithm to execute in practice. In the old days, and perhaps not very old, POMDP problems, to solve exactly POMDP problems was nearly impossible. You had to have something like 7 states, 8 states was the maximum that you could deal with. 7 states, not 7 state variables, mind you, okay? 7 states, a discrete state, a finite state system with 7 states. That was the maximum that you could go. And the reason for that is that a 7-state discrete state system with 7 states, when you formulate into the space of belief states, then it becomes a 7-dimensional simplex, right? You have a 7-dimensional probability distribution. And that's an enormous state space to calculate backwards by the dynamic programming recursion. Now, the amazing thing that with approximations, reinforcement learning ideas, and the ideas that we're going to discuss later in this course, we can solve problems that are of astronomical number of states. Thousands, millions, whatever, okay? It's a tremendous improvement on the state of the art on POMDP problems at the expense of approximations. We're going to discuss later rollout ideas, approximation in value space, and you'll see how all this works out in the context of specific applications. Of course, the application has to have some structure to take advantage to be able to solve such large problems, as is always the case in dynamic programming. But we have made tremendous progress from the time of 7-state limitation. Yeah.
Resources are required for those higher order applications? Are we talking supercomputer or is it something that?
No. It's Yuchao can tell you more about that because he has done a lot of computations with POMDP, talking about personal computers. And later on, I'm going to give an example of a POMDP problem involving the Wordle puzzle, the New York Times Wordle puzzle, where the decision at every step, it requires only a few seconds, like 2 or 3 seconds, to execute an approximation to this algorithm. And the Wordle puzzle has a state space that's enormous. XK, you'll see later, is a huge state space, combinatorially exploding state space. Despite that, with clever reinforcement learning and approximation techniques, we can deal now with problems like that. Okay. So now let's go into problems with changing parameters and adaptive control. Adaptive control is a field that has a long history. It goes back to the 60s. And it has to do with situations where you don't have a system that has, the system is not stable. It changes all the time. And let me give you an example. Cruise control. Here, we want to keep the velocity of a car on a highway close to some target level, X bar. So you want to keep it at 60 miles, let's say 60 miles an hour, and the car may accelerate or decelerate for some reason or other, and the cruise control brings it back to X bar. So this is oversimplified, and let's model the car velocity by this equation, the evolution of the car velocity. Xk is the velocity at time k. Let's assume a linear model where A here is a damping factor, less than 1. It models friction on the road, okay? That the friction on the road tends to reduce velocity. Also, wind drag tends to reduce the velocity, and there may be other things too. Like the condition of the road, okay? B, the B term, this control term is the propelling power for the car. Either gas, press the gas, move it forward faster, or press the brake to reduce the velocity. However, this B coefficient depends on a lot of things. It depends on the conditions of the road, depends on whether the road is going uphill or downhill, depends on the number of passengers in the car. So A and B, okay, so let's complete the formulation. The cost per stage is to keep the velocity close to X bar. So let's say there's a quadratic cost on the deviation from the current, from the target velocity. And there's also a cost that penalizes you taking positive or negative values. So we don't want the car to, controlling the car to be too jerky, okay? You want the acceleration and deceleration supply to be relatively smooth. And we assume that R is given. However, A and B are not known. In fact, they are changing all the time. And they may be measured online, perhaps, with some error, however, because instruments are not perfect. So we don't know some of the models of the system, some of the parameters of the model, and these parameters may be changing. So that's the kind of situation that you have in adaptive control. In robotics, just about every robot faces an adaptive control problem, because to take something from here to here, it depends how heavy. The model depends on how heavy this is. Or a car that's driving, a self-driving car, the conditions change. Other cars are in there, obstacles, bends on the road, and so on and so forth. So this is a very important class of problems. and difficult to deal with, and people have been trying to address them since the 60s. Now, we are going to discuss briefly 3 approaches towards these problems. The first approach is just to ignore the changes of the parameter and hope for the best. In other words, design a fixed controller that is robust in the sense that it works for a broad change of parameters. Okay? That's one possibility. Another possibility is to try to estimate the parameters online, try to learn them, and then use these estimates to modify the controller. And an important idea here is to do online replanning by optimization and re-optimization. In other words, modify the controller online and make it optimal for the current set of parameters, your best estimate of the parameters. And as these estimates change, modify the controller in response. This is sort of like a certainty equivalence approach. You treat the parameters as if you know them exactly, but in reality, they are not. They will change over time. Another possibility is to do the same thing, estimate the parameters, but instead of replanning by optimization, replan by approximate optimization, in particular by some kind of a rollout policy that takes into account the changed parameters. And this base policy may be something like a robust policy that you use to do rollout, but the rollout takes into account the re-estimated values of parameters. So this is a simpler version of this, a simpler re-optimization. It's approximate. The third approach formulates the adaptive control problem as a POMDP, whereby the unknown parameter is treated as a variable to be estimated. And we have a belief state over the current set of parameters, and you formulate the whole thing as POMDP. That's also an old approach. It dates again to the 70s at least, if not the 60s. And we're going to discuss this one and these two briefly now. Any questions? Okay, so let's go into robust control. Here we have a system. It's changing all the time. It gives some output, perhaps the state or perhaps some function of the state. And then we have a fixed controller. We don't try to estimate the parameters. Controller is fixed and provides a control. So we ignore the changes in the system, and we make no attempt to estimate or learn them. And what we hope here is that this fixed controller will yield acceptable results throughout the range of system changes. Okay? So this is sort of a simple, kind of optimistic approach, but there's an important time-honored successful example of this approach, which is PID control. Perhaps you have heard of that. PID starts proportional integral derivative, and it's a 3-parameter controller. One multiplies the proportional term, another the integral, and another the derivative. And you tune those online for the given system. So you have some chemical process control, and then there's a technician goes in there and tunes these parameters until the process sort of works properly. Of course, there's history of good parameters and so on, but that's the way this works. However, there are some difficulties with this. The first is that it primarily applies to single input, simple output case. So there's a single input, single control, and a single measurement. So you measure, let's say, the position, but not the velocity of something. And it's only one variable in, one variable out. So that's a limitation. And but the great advantage is that there's no need for mathematical model of the system for this controller. That's a huge advantage. Not only you don't need to track the parameters as they change, but also the system itself is unknown. You just don't care at all what the system is. Of course, it has to fit the proper type of system for which this PID controller is successful. PID control has been applied to many applications. It goes back more than 100 years. And it was not replaced as the mainstream control system until the 60s, when the state variable models started becoming available, and gradually they have taken over the research scene because they are more general and they take better advantage of the available computational resources these days. So robust control. And the next type of optimization of adaptive control is called indirect adaptive control. That's the name of this in the literature. And it does online replanning by optimization. So you have a system, it has a state in the control, and also it generates some information that tells you something about the current parameters. The parameters are estimated, they're fed into the controller, and the controller is re-optimized in response to the new parameters. So there's a two-phase alternation. You identify the system, learn the parameters, and then you re-optimize the controller. You work for a while, figure out what the new system is, and then re-optimize the controller and repeat. In the artificial intelligence literature, this system identification is the control name people that control theorists and system theorists use. In artificial intelligence, people talk about learning the environment, okay? You'll see this term. We learn the environment and then we reinforce signals, okay? Something like that. It's very different terminology than the terminology of control theories, but it talks about the same thing. Generally speaking, learning the environment and learning how to react to it is a very difficult problem in reinforcement learning, in artificial intelligence. The optimists in this field talk about a robot going into a room with cameras and figuring out what the environment is, where the doors are, where the windows are, where the refrigerator is, and so on, and then picking things and pulling out a vacuum cleaner from a closet without knowing anything about the room, okay? Just figures it all out, learns the environment, and then does useful things. Okay, so this is the same thing as adaptive control. It's no different. It's just a more optimistic view and a more computer-oriented learning view of the problem. So, of course, to implement this system, you need to have a parameter estimator and a re-optimization of the controller so that it's optimal for the current set of parameters. Now, this can be time-consuming. This re-optimization can be time-consuming. It has to solve a dynamic programming problem to optimize. Again, a new dynamic programming problem. This is difficult to do fast enough. So there are some serious issues. There are also some serious issues about the theoretical issues about the system, whether you can identify the parameters simultaneously with doing control. And control theorists have worked quite a bit on this. There's a question of identifiability, whether the control may mask some of the values of the parameters and the system may become non-identifiable in the presence of control. All of this takes us far afield into the theoretical landscape, and we're not going to talk about this, but you can look at your textbook to get more information. So this is indirect adaptive control. Learn the system, re-optimize the controller, and do it again and again as necessary. So let me give you an example here, a comparison between robust control when you don't re-optimize and online replanning where you do re-optimize. So this graph relates to a linear quadratic problem with one state variable. And this B coefficient here changes over time. There's a quadratic cost. And now we use a robust controller that's optimal for the value B equals 2. Okay? But then B changes, and therefore the performance of this robust controller also changes. And I have plotted here the cost coefficient of the robust controller, the one that's optimal for B equals 2, but for other values of B. And you see the performance deterioration. The optimal cost for a given value of B, if you were to re-optimize it, is the bottom curve here. And the robust controller that's not sensitive to changes in B is this one here. For values of B close to the nominal value for which it was designed, 2, it performs pretty well. But there's a performance gap as B gets away from the nominal value. Okay, so that makes sense, and that's typically what happens with robust controls. They work well if the parameters stay close within some acceptable range, close to what the robust control was designed, and then you get rapid deterioration or instability in more serious cases. Yeah.
So when you read the graph, the fact that one approach versus the other, the learning is much faster versus slower? Or?
Here we assume that learning is infinitely fast. In other words, the assumption for this figure is that there's no gap as the parameters change, you learn them instantly. Okay. There's no gap. Of course, if there's gap, then all sorts of bad things can happen. Now this curve, this will not change, of course, because it doesn't use any estimates of the parameters, but the bottom curve will change because of the lags in estimating the parameters. Okay, so one of the disadvantages of indirect adaptive control and online re-optimization is that it can be slow. So we can use an approximation. Instead of optimizing the controller for the new parameters, we use a rollout approximation, for instance. So what do we have here? We use some kind of robust policy as a base policy for rollout. And the rollout scheme looks like this. You've seen this before. At the current state, we look at all the possible next states, do rollout with a robust policy for the changing system, and you get to know, again, the changes in the system, and then you do a cost function approximation at the end. So rollout takes into account the new parameter estimates in the look-ahead optimization, but does not re-optimize. So it does it much faster. So we continue to use the same robust policy, and possibly in the background, you may recalculate the base policy to improve the system with the aim to improve the system. So that's the difference between the rollout approximation and the full-fledged indirect adaptive control by re-optimization. And now let me come back to the same example. Scalar system, quadratic cost, B is changing. The robust controller, which is also the base policy for rollout, is designed to be optimal for B equals 2. And we change B and see what happens. The robust base policy does like that. The solid line is the exactly re-optimized policy. And what you see here as orange stars corresponds to the approximated re-optimized rollout policy. Rollout does almost the same. as the optimal at much lower cost. And what you're seeing here is what I was talking about in last lecture about Newton's method, the effect of Newton's method. It brings the performance of the rollout controller almost optimal if you are within the region of convergence of Newton's method. So that's all I have to say about this methodology of online replanning by reoptimization and rollout. Are there any questions? Okay, so now let's take another approach to adaptive control, which is based on POMDP. Here, we assume that there's an unknown parameter theta in the system equation that we do not know, and it may change. And for the purpose of this presentation, we assume that the system is deterministic. It doesn't have to be. And it involves a right-hand side dependence not only on xk and uk, but also on theta. And we assume here also that theta has can take a finite number of values, but otherwise is unknown. And we view theta as part of an augmented state. Xk and theta is the pair xk, theta is the augmented state, which is partially observed. In other words, we take measurements here, and we estimate this theta online, and then our state is xk and theta, and there's a belief state associated with theta. In other words, with an estimator, this belief estimator, we calculate the probability that the parameter is theta given all the information that we have, okay? So we assume that we have a belief estimator that generates these probabilities. And then the exact dynamic programming algorithm for this problem here is a POMDP dynamic programming algorithm that has this form. Optimal cost to go given the information is equal to the expected cost of the first stage plus the optimal cost from the next stage where you land. However, the state of the POMDP is the entire information vector here. And the expected value is taken with respect to these probabilities, the components of the belief state. Intuitively, this algorithm makes sense. To justify it mathematically, it takes a little bit of thinking, but there's an explanation in your book and also the literature that is cited there. And I'm not going to go into the explanation. Again, this is expected value of the next stage weighted by the probabilities that the parameter has value I. And remember that there are m possible values of the parameter. So this is a summation over m terms, a weighted sum with m terms. And this is also something that is also an expected value weighted by these probabilities. Okay. Now, this dynamic programming algorithm is extremely difficult. It's very difficult to carry out. Because it's defined over the space of information vector, and God knows what this information vector is and how difficult it is. However, it's possible to apply approximation in value space, replacing J star by some J tilde. And the type of J tilde that works is for each value of the parameter, have some function that depends only on the next state of the system. Now, this simplifies things a lot in this equation in this minimization. And once you minimize over UK, you obtain a one-step look-ahead policy. Not that it's easy always, but it's greatly simplified. Now, an example that's interesting here is suppose that you have, for each fixed value of the parameter, you can optimize this problem and get a cost function. Then you can use this as your J tilde I. Optimal, assuming that you know exactly the value theta to be theta I. Another simpler example is J tilde I is, instead of being the optimal, the optimal cost, being the cost function of a known policy instead of the optimal policy, assuming that theta is theta I. And this is rollout, basically. Okay, so that's this approach. It's not a cure-all approach. It does not apply to all situations. It applies to specific situations that have a structure that's favorable for it, like everything else in reinforcement learning. You have to find the right method for your given problem. Are there any questions here? Okay, so let me illustrate this approach with the Wordle puzzle. How many of you know about or have played Wordle? But okay, half of you something. Okay, I'll explain for everyone what this is briefly. The word puzzle appears every day on the New York Times, and millions of people play it every day, and it tries to guess a mystery word. There's a mystery word that's selected each day from some mystery list. That list in the New York Times case is like 2,300 words. A certain list that's available to you, and you have to guess what's the word of the day, okay? And you do that by asking questions, making guesses to the system, and you get answers. And okay, let theta be the unknown mystery word here, okay? 1 out of 2,300. Select according to some distribution, which in the case of New York Times is uniform, I believe. UK is your action, the guess word that you select at time k, and you have only 5 guesses in the case of Wordle. And now xk for us is going to be the list of possible mystery words given the guesses so far. So initially, x0 is a list of 2,300 words. After you make your first guess, this list is reduced. Let's say 1,000 words. After the second guess, it's reduced to, let's say, 500 words. And the objective is to get it down to one word, make xk to have a list of consisting of one word after 5 guesses, okay? So big list becomes a smaller list, and so on. And hopefully by the end of the horizon, 5 guesses, it has shrunk to 1. That's when you have guessed exactly the word. And now, okay, let's say a few things about how the game works and how these guesses, what's the feedback that you get from these guesses. Here, the mystery word is this word here, inert, okay? And suppose that, of course, this is unknown to you. This is the theta that's unknown. And you get a measurement, you select the measurement to be this first word, audio, as an example. And the measurement that you get, the feedback that you get, has to do with the commonality of letters between the guess word and the mystery word. And if there's a common letter, it's indicated here. And if it's not in the same position, okay, I colored it by orange here, yellow. Okay, so that's the first measurement. The list has shrunk now. xk has shrunk to we exclude all possible mystery words that do not have any I in them, okay? Now, we take a second guess. Let's say our second guess is this word here, stern. Now, stern and the mystery word have a lot of common letters, have 4 common letters. There's a T in a different position, so it's colored by yellow. There's an E and R in these positions, which are the correct positions, and they're colored by green. And there's also an N in the wrong position, colored again by yellow. So that's our action, select stern, and the feedback that we get is this green and yellows, okay? Now, at this point, I have received these two measurements, and I have guessed all the letters. I know what the 5 letters are. They're I and then T-E-R-N. And okay, you use your imagination here, and it's fairly easy to guess that the next word is inert. So your score here is 2. You have been able to, or 3. You have been able to guess the word in 3 guesses. Okay, so now how do we formulate this mathematically? Theta, remember, is the unknown mystery word we viewed as part of the augmented state. XK is the list, theta is the mystery word, and we estimate a probability distribution on that given the feedback that we have gotten already. And we're going to see how a rollout algorithm works for this. And by the way, this is joint work with 2 of the students in the 2022 offering of the class, Siddhant Bhamri and Amrita Bhattacharjee. And there is a paper, there's a conference paper and also an archive paper that you can find online. And what we have done here is apply rollout with with a base heuristic. And we have used 2 or 3 different base heuristics, which are common in the literature. In other words, people have developed heuristic ways of solving the Wordle puzzle. And we have used this as base heuristics in a rollout scheme, okay? Look at all the possibilities, run the base heuristic, select the one that's best. Except that the possibilities in our case are many, okay? Because the number of guess words, legitimate guess words, I think is like 12,000 or something. So we have a control space that has 12,000 components. So we have a fast heuristic that prunes out these possibilities and obtains the top 10 or top 20 choices. And then we roll out from these 20 using the base heuristic and find the one that solves the problem that solves the problem in minimum number of steps. So I'm going to give you computational results later in a lecture that's several lectures ahead of today. But just as an example, the optimal performance for the New York Times puzzle has been estimated as 3.5 plus average number of guesses. In other words, if you were to use an optimal algorithm, which assumes, incidentally, a uniform probability distribution over the selection of the unknown mystery word, then that's the optimum. And you can do this by dynamic programming. You can calculate this by dynamic programming, taking also advantage of the special structure of this problem to accelerate the dynamic programming algorithm. And this requires you, I don't know the exact time, but it appears from what has been written, it requires you several days and parallel computation to do it. However, it has been done. And now what we have done is use rollout with a simple heuristic, and we lose less than 0.5% in performance. On the other hand, online, our algorithm gives you an online answer within seconds on your personal computer. So it's a tremendous reduction in computation time with a minimal loss in performance. What's very interesting also here is that we have tried 3 heuristics. 2 of them are pretty good by themselves. They give scores of like 3.7, 3.8, something like that. And we reduce this to something that's close to the optimum. But there's one heuristic that's pretty bad, okay? And it gives you a performance that is like 5, okay? Instead of 3.5, 5, more than 5. the interesting thing is that even with this crummy heuristic, we get a rollout performance that's pretty close to the optimal. It's not quite this, but it's like 3.6, 3.7, something like that. So that highlighted a property of rollout that I have mentioned in the past, namely that you don't need to have a great base heuristic in order to get good performance. What is important is that the performance of that heuristic lies within the region of convergence of Newton's method, okay? And unfortunately, you can't know what the region of convergence of Newton's method is, but you can try even a bad heuristic, and surprisingly, you will see great performance still by the rollout algorithm. And that has been a manifestation of that. Let me also finally say that this optimal calculation would not be possible if you complicate just a little bit this problem. In other words, suppose that instead of a uniform probability distribution, you have a non-uniform probability distribution, some words more likely than others to be selected. Or you change from 5 letters to 6 letters, okay? Then calculation of the optimal, it may take you more than your lifetime. Okay? It's a very, very hard computation. Rollout is not affected by much. It's affected some, but not by much. It's still a feasible computation. So that's the nice thing about the suboptimal methods. They scale with problem time, with problem size, whereas the optimal calculations may not, usually do not. Okay, are there any questions? Okay, so we'll take a break for 15 minutes and then come back with model predictive control.
Okay, let's get to the next topic of this lecture, which is model predictive control, which I will refer to as MPC. This subject is dear to our heart, both to me and to the professor, because actually the professor in his PhD thesis, he has done some introduced some fundamental concept and methodology that is the core, still remain to be the key component in today's MPC methodology, which is 71, so more than 50 years ago. And in my thesis, I have done something related to the design of terminal cost and so on, and discussed the connection of MPC methodology with dynamic programming. So, and the reason I have done that is because MPC is one of the most popular, if not the most popular control methodology in control theory. But before we get to MPC, let me just give you a brief review of the control theory. We have talked about this figure and so on, but basically control theory deals with systems where the state typically is a multidimensional state, and each component of the state is taking values from continuous quantity, take values from some real line and so on. And it could be a mixture of continuous and discrete component as well. And the classical control problems are 2 types. The first type is a regulation problem, whereby you want to design control such that the state remain close to in the vicinity of a reference point. And the other type is a tracking problem, and you are giving some reference trajectory and you want to have the state to track the trajectory. For the first type of problem, the regulation problem, we have talked about this academic example, whereby the practical goal is to have the rod with a mass at the end of it to be vertical. So for this problem, the state is defined as the angle between the rod and the vertical line and its derivative. Of course, in this course, we only deal with discrete time problems, so you may discretize it. And the control is the force you put on the card at the end of the rod, and you want to have the rod maintain vertical. And historically, the reference point is typically set to 0. And despite being an academic example, it's actually not trivial to design controller for this system. You can give it a try. Basically, if you have some pen or have some bar, you put on your palm and try to move your hand back and forth in order to have the rod stay vertical. A regulation problem emerges in almost all aspects of our daily life. For example, this afternoon, I went to swim, and the temperature of the swimming pool is set to some constant number, which is different from the ambient temperature. And so the control in that context is to pull in some hot water to make sure the pool temperature stay close to the set point despite the difference between the ambient temperature. And yeah, so regulation problems appears in almost all aspects of our life. The second type of problem, which is the tracking problem, or path planning, as someone would refer to, is starting from some starting point and with some target position, we are giving a reference trajectory. We want to design controls such that the system state stay as close to the reference trajectory as possible. Within this context, there can be various constraints emerge, including fixed obstacles. And if we use this vehicle example, there would be vehicle velocity constraints, acceleration constraints, as well as moving obstacles, which we do not know beforehand. As a result, the problem that we discussed about, like the linear quadratic problem, is often inadequate. And the reason is in linear quadratic problem, the best we can do is just put a quadratic term on some state which we hope that the state does not go to. And that can be viewed as a form of soft constraint. So you penalize some state by a big cost. But in some cases, like the autonomous vehicle context, you don't want to put a price with the car crash. You just want to make sure the car does not crash, right? So you need to have hard constraint, and to deal with the state and control constraints is very important. And that's one of the reasons that MPC is so popular nowadays. And another important aspect is that it allows online replanning, the MPC methodology. So if we compare this problem with the problem addressed by AlphaGo, AlphaZero, and so on, even though AlphaGo or AlphaZero is quite remarkable, but what is favorable in those problems is that the rule of the game does not change, so you can count on it. Whereas in reality, if you design autonomous vehicles, well, you don't really know what's going to happen. It may happen that on the road there would be a deer appear, or there would be a bear appear. So something unexpected may happen, and you need to deal with those kind of situations. And that makes this type of problem even more challenging. Regardless of the tracking problem or regulation problem, model predict control has emerged as one of the most popular approaches to deal with those problems, and at least one of the most researched even till today. And to illustrate, we're going to consider a deterministic infinite horizon optimal control problem, whereby it involves a stationary state system equation. So f of xk and uk determine completely the next state xk plus 1. And the cost per stage are non-negative for all xk and uk. There is a stage cost which is stationary and non-negative. And suppose that our goal is to drive the system state to 0. So it's a regulation problem. And suppose further that if the state is 0, xk is 0, and if we apply uk is 0, and it can remain at 0. And a sensible choice for 0 and 0 here would be the stage cost here is also 0. So it's only 0 at the reference position, and positive anywhere else. So the practical goal is to keep the system state at origin, and there is no discount. So for this regulation problem, we're going to introduce a form of MPC, which dates back to the late 80s, and 88 more specifically. And we will argue that it can be viewed as a form of approximation in value space. So this form of MPC, suppose that currently we are at state xk. So what we do is we minimize the cost function over the next L stages, while requiring that after L stages, the state reaches origin exactly. So we consider essentially a finite horizon deterministic optimal control problems involving L stage control. And we want to find a control sequence that minimizes this L stage cost, and at the same time to make sure at the end of the trajectory, the state reaches 0 exactly. At the current state xk, after solving this problem, we're going to apply the first component of the optimal control that leads to the minimizing cost, while disregard all the other controls. You may know that by what according to my description, it sounds very similar to approximation in value space we have discussed earlier, right? Indeed, it is a form of rollout. It can be viewed as a form of rollout, whereby it involves one-step lookahead with a heuristic that starting from xk plus 1, this heuristic requires the system state to reach the origin in L minus 1 stages and stay there afterwards by applying control u equal to 0 afterwards, and minimizing the cost of this L minus 1 stage. So that's the base heuristic in this one-step lookahead rollout scheme. So it can be viewed as a rollout with this special base heuristic that minimize the control cost such that it drives the state to 0 in L minus 1 steps. As mentioned earlier, this is well suited for online replanning. For the moment, we neglect the state constraints. So we suppose there's only control constraint or some challenges in system dynamics and so on. Later on, we're gonna go back to the state constraint, go back to the point of state constraint. So, but back to this problem, this infinite horizon optimal control problem with non-negative stage cost. We actually have solved some special cases of this problem exactly, which is the linear quadratic problem, right? So in the case where the system is linear and the cost is quadratic in terms of xk and uk, this infinite horizon optimal control problem can be solved exactly. But since turns sour quite quickly if we make some modifications such as adding constraints on the control, so it's not possible to have as large control as you want, or if the system dynamics is not linear anymore. And those motivates the use of this suboptimal MPC control methodology. Another point I want to make is this scheme can be viewed as rollout with this special base heuristic. Alternatively, you may consider this constraint that require the state to reach 0 after L stages. You may consider it as a special form of terminal cost approximation, whereby it is 0 at 0, this J tilde equal to 0 at X equal to 0, and infinity anywhere else. So in this interpretation, this MPC can be viewed as L-step lookahead with a special form of terminal cost approximation. And this interpretation brings me to some natural extensions of the MPC formulation discussed earlier, whereby instead of requiring the terminal state to be exactly equal to 0, we may introduce some terminal cost approximation, G, and instead of solving that problem, the problem that requiring the state to reach 0, we may solve this problem. So it's again, L stage minimization problem and a terminal cost G function we define. And in the special case, as I said, if this G function is equal to 0 at state 0 and infinity anywhere else, then we recover the previous formulation, right? So if we look at this figure and just ignore this blue box for the moment, it's L-step lookahead minimization with a terminal cost approximation. And this is common variant of MPC. We use a non-negative terminal cost G in the L stage MPC problem instead of driving the state to 0 in L steps. Again, as mentioned earlier, this can be viewed as approximation in value space with multi-step lookahead. Now, if this terminal cost approximation is not so good, or if this minimization is too difficult to solve, and you can only afford solving minimization, let's say L equal to 2 or not sufficiently large, you may supplement it by introducing this gray box, this blue box, which is M-step truncated rollout. So instead of do a long minimization, you may cut short the minimization and run some rollout simulation under a policy. And the important point here is the policy has to be stable. This base policy used in rollout has to be stable. And at this point, if you look at this figure, this is identical formulation or structurally identical to the AlphaGo TD gamma architecture, right? The difference here is, okay, as I mentioned earlier, control theory typically deal with state that is involving continuous quantity. So in the AlphaGo TD gamma type of application, what you do when you solve this minimization problem, you enumerate all the moves and counter moves, and then run the simulation, and then compare those numbers that you enumerated that corresponds to different moves in the game. Whereas in the context of MPC, you need to solve an optimization problem which involves primarily continuous quantity. The good news is typically there are available solvers, both commercial or open source in various languages that you can use to solve this type of optimization problem. And it's especially so if the system is linear, the cost is quadratic, and there are some constraints on the state and on the control and so on. This can be routinely solved within milliseconds. So, so don't feel intimidated if this minimization involves some continuous quantity. This is there are some very mature tools you can use. As I alluded to, that the problem may also include state constraint, in which case we obtain one of the most general forms of MPC, as I will introduce shortly. So within this context, an important question one need to answer in designing this general MPC methodology is whether or not the obtained policy computed by this multi-step look-ahead minimization. Remember that suppose you get some control sequence, u tilde t equal to k plus 1, k plus 2, until k plus l minus 1. You're going to apply ut, the first component of that minimizing control sequence, and disregard all the others. Conceptually, you can view this minimization as defining a policy, which we refer to as MPC policy. And the question you need to answer is whether or not such an MPC policy is stable. And in fact, this is the question somewhat you have answered if you have done the homework, the latest homework. So essentially, if we look at this simplified case with linear system, quadratic cost, and no constraint on state and control and so on, this G function need to be chosen from the region of stability you have calculated in your homework. And as you may recall, the region of stability increases with larger L compared with one-step look-ahead, right? And in fact, it can be enlarged with truncated rollout as well. So for those of you who are interested, you may want to also try to calculate, suppose that you have obtained a stable base policy, you can check whether or not this form of L-step look-ahead minimization and M-step truncated rollout with a stable base policy, whether or not introducing this portion enlarges the region of stability. And that's an interesting exercise for you to try out. Yeah.
Why is that linear?
Okay, so that's an interesting question. So model means that you need to have a system dynamics model, this system equation f of xk and uk, right? Predictive means you look multiple steps into the future, which are doing prediction and control. So there are other names, and nowadays there are methodology still bearing name of model predict control, but use data to represent in a way the model. But it's, in any case, you need a model in order to do prediction, and then based on the prediction to select control. So that's how the name is come up. Okay. Now let's get to the important question that I have not answered yet, which is how about problems involving state constraints? It is often important to deal with additional state constraints of the form xk belongs to some set, where this set is some subset of the state space. Then the MPC problem to be solved at the k stage must be modified. The reason is, assuming that the current state xk belong to some constraint set x, then this MPC problem need to introduce this constraint to make sure that your predicted future trajectory all belong to the same state constraint. And this is quite sensible. I mean, using the autonomous vehicle example again, and you want to make sure that your vehicle stay on the road in your prediction, like 5 seconds into the future, right? So the control UK tilde thus obtained is required to generate a state xk plus 1, the next time instant state, which still within this control constraint set. However, it is not easy to just pick up some obvious choice of constraint and use it within the MPC architecture. And the reason is some obvious choice may not allow you to have a feasible solution in this example. We will get to that point shortly. So there are also approximations to this constraint. So it's an important question to design such constraint so that the MPC problem can be feasible and remain to be feasible in the future stages. And there are also approximations to this form of state constraint using control barrier functions, which is very popular nowadays, and they are computationally more convenient in some context. Okay, let us use a very simple one-dimensional example to illustrate the idea. Suppose that in addition, consider this system equation, the system dynamics, where xk plus 1 equal to 2 times xk plus uk. And in addition to the system, we introduce a state control constraint, which is the absolute value of uk can be no more than 1. All right. So then we want to design a state constraint set of this form, where x at each stage, the absolute value must be no more than this design parameter beta. Now let's look at various situations of beta. And as before, our goal is to, let's say, want to make the state goes to a region or stay within this control constraint set. So if beta is bigger than 1, then what's going to happen is within this state constraint set, we can find some state such that in just one step, it's not possible anymore to, regardless of your control choice, it's not possible to have the next state of the next time instant to remain within this constraint, state constraint set. So if beta is bigger than 1, the state constraint cannot be satisfied for all initial state x0 in the x. And the reason is, suppose that we choose the initial state x0 equal to beta, where beta is larger than 1. Then given that the state is amplified in this state equation, then the next time instance, the x1 equal to this form, where this term is 2 beta. So regardless of the choice of u0, you're going to have x1 larger than x0. Consequently, this argues similarly, the entire sequence of the generated state will goes to infinity as k goes to infinity. So this simple example demonstrates that you cannot just randomly pick some state constraint that seems natural and use it in MPC. That is not sufficient. So if you want to have all the future state remain within this constraint set, it is only possible if beta is no more than 1. In the extreme case, if beta is equal to 1, it's still possible to have all the future states remain within the set. And sets of this property that starting within the set, and you can find some control such that the state can remain inside the set, are called invariant. And this concept, as it turns out, it's possible that you can use certain form of algorithms to compute such a set or approximations of this set, the subset of this set. And this is part of Professor Basica's PhD thesis. For those of you who are interested, then take a look. Okay, so, and this brings us to this important concept called invariance. The invariance requirement for the state constraint involved in the MPC. To guarantee the feasibility of MPC problem with state constraint xk belong to this state constraint set for all k, an invariance condition must be satisfied by x. That is, for every x within the set, there exists some control such that f of x and u still belongs to this x, this set. So let me give you a more elaborated example, again, using the autonomous vehicle application. You know, in some country, the highways, they don't have speed limit. So you can drive as fast as you want, and as long as it's within the capability of your car. And if you design autonomous vehicle algorithm within such a case, in such a case, it's a bit tempting to design a state constraint, which is the just the boundary of the road, right? Suppose that your autonomous vehicle algorithm deal with both acceleration and steering. So you may think, okay, it's fine to just design constraint as the position of the vehicle so that it remains within the boundary of the road. So no constraint imposed on the velocity. But suppose that your car, the car is going to a turn, and if the velocity is quite high, then regardless of how hard one brakes, the car may still get out of the road. So that design choice is not, if you design the control, or if you design the state constraint that only involve the position of the vehicle, not velocity, then naturally there may be some situation, there may be state velocity and position combination that does not allow you make sure that the vehicle remain on the road. So that's what we mean here by invariance. So you need to design a state constraint such that there exists some control to make sure the next state remains within this state constraint set. So how do we compute an invariant subset of the given constraint set? And as mentioned, that this is necessarily an offline calculation because it involves a lot of computation. As it turned out, given a state space X, there exists a largest possible invariant subset of X, so that starting from anywhere within the subset, you can find a control to make the next time instant state remain within the set. And it can be computed in the limit with an algorithm that very much resembles value iteration. As I mentioned earlier, that such algorithms also applies to problems where there are some disturbances, which is bounded. And there are also other simpler possibilities for computing invariant subset of X. So you may compute some subset of this largest invariant set and apply that to MPC, which would also work. Okay, so at this point, we have completed our 4 overview lectures of the course, where we have aimed to provide an overview of the approximate dynamic programming and reinforcement learning landscape. And our goal is to provide a foundation for deeper development of other reinforcement learning method that are going to be covered in the future lectures. And also more important, equally important is to get you started on your term paper. So hopefully with all those 4 overview lectures, you have a rough understanding of where we are heading to, and you can start preparing and thinking about what you want to work on for your term paper. We have described in varying levels of depth the following ideas: the algorithmic foundation of exact dynamic programming in all its major forms: deterministic, stochastic, discrete, and continuous, finite, infinite horizon. Approximation in value space with one-step and multi-step look ahead, which is the workhorse of reinforcement learning. It also underlines major success stories, including AlphaZero and earlier TD Gamma. The fundamental division between offline training and online play in the context of approximation in value space have been elaborated. As you may notice that those 2 major components are somewhat decoupled. So you can choose whatever you feel suited for the problem at hand to do offline training. And then in the online play operation, you may use various combinations or various possibilities to do the online play, perform the online play operation. And we highlighted the synergy of those 2 algorithms through Newton's method interpretation of the approximation in value space. So the fundamental method of policy iteration and rollout are emphasized, the former being primarily an offline method used to learn a base policy or a cost function approximation, whereas the latter being primarily a less ambitious online method used for in the real-time operation. They are connected with Newton's method as well, in which case exact policy iteration is full-fledged Newton's method for solve the problem, the Bellman's equation, whereas rollout is one step of Newton's method. And we cover some major models with a broad range of applications, such as discrete optimization, POMDP, multi-agent problem, adaptive control, and model predictive control. And the point we want to emphasize is that regardless of the, despite all the diverse nature of the problems covered, the core, the structured property of those problems are the same, which is the principle of optimality for all those problems applies despite the diverse nature of the state and control spaces, and the view of Newton's method, the view of approximation in value space as one step of Newton's method applies. So the difference here is when you're facing different problems with different form of state and control and so on, you may need to use different tools to solve some of the problems, like how do you solve this offline training problem, what function approximator you use to approximate this optimal cost to go, J tilde, do you use some quadratic function or you use a neural network? And another thing is, how do you solve this online minimization problem? Do you use some optimization solver available, or you write code by enumerating all the controls? So those are the differences, but those differences does not affect the fact that the principle of optimality applies to all those problems, and the view of Newton's method for the approximation in value space. The use of function approximation, which has been a recurring theme in our presentation, we have hinted at several points some of the principal schemes for approximation based on neural network and feature-based architecture. And in our future lecture, we're going to also talk about the new form of neural network, which is, as you all know, the transformer I mean, it has revolutionized the whole field, and we can demonstrate two cases, case study of how the transformer can be fitted into the scheme, both as the base heuristic in the rollout scheme, but also as cost function approximation, and we're going to demonstrate how they can be applied within our approximation in value space. Yeah. So feature-based architecture, if you look at the neural network, suppose that you have a neural network and you want to use it to approximate the cost function approximation J tilde, right? And if you look at the output, suppose the output of the neural network is a real number, is a scalar that give you the cost function approximation. Then the layer before the output can be viewed as features of this problem, right? But this is automatic feature construction. And in old days, one may need to construct features themselves using expert knowledge and so on. For example, in earlier application of Tetris, to solve the Tetris problem, some computer game problem, then the state space is too large. You need to craft some features based on your experience with the game, like what is critical. There are some holes on the wall and stuff like that. And so those are manually crafted, and using your network, all the features are automatically constructed. Okay. Let's provide an overview of what lies ahead and what we will and will not cover. What we have covered is basically the first chapter of the textbook, which provides a foundational platform for exploring a deeper level various algorithmic methodologies, such as rollout, its variant, and its application, including discrete deterministic problem, multi-agent problem, and so on. And this is covered in chapter 2 of the textbook. And sequential decision-making in special contexts involving changing system parameters, sequential estimation, Bayesian estimation, simultaneous system identification and control, again covered in chapter 2. And in chapter 3 of the book, it talks about offline training for approximation in value and policy space using your network and other approximation architecture, including some problem approximation, and one of the topics that we will cover in the future lecture. Stochastic algorithms, such as temporal difference method and Q-learning, used for offline policy evaluation in the context of approximation, approximate policy iteration. We will not talk much about this type of methodologies. So in general, we de-emphasize the statistical aspect of the reinforcement learning method. For one, we have a lot of material to cover. For two, it involves a lot of complicated statistical analytical devices, which we decide not go to too much depth. And the sampling method to collect data for offline training in the context of cost and policy approximations. In the textbook, there are some material on it, but it's not the focal point of our course. Statistical estimation and efficiency enhancement of various sampling methods used in simulation-based schemes. So some of the methodology, some of the cost function approximation calculation relies on simulations, and in the subsequent applications, we have used methodology which essentially just collect as many samples as possible within the time limitation that you can afford. And that's straightforward and easy to do, compare with using advanced statistical devices to to do exploration and so on. So therefore, we won't go deeper into those topics either. And a deeper exploration of control system design methodologies such as model control, its applications in robotics and automated transportation is a vast field, and it's an expanding field as well with a lot of applications and so on. And of course, we cannot get full-fledged development of this subject either. About your term paper, we offer two choices. One is a mini research project, which we encourage all of you to try at least. You can team up to 3 students to try to find a research subject that intersect with your personal interest, your research project at hand, and the material covered in the course. So, the goal is not really to reproduce an article you found online, the experimental result of an article you find online, but rather try to come up with something new, use the ideas covered in the course. You may develop some of the ideas mentioned in the course and apply it innovatively in a new context, or come up with new ideas, new methodology. The second option is read and report. We ask you to provide a critical synthesis of 2 to 3 related research papers that is related to the course content, and based on your understanding of those research papers, you write 8 to 15 pages. And it's possible that you can start with a mini research project. And I mean, doing research is taking a lot of risks, and there's a lot of unknown. So research by definition is you don't know before you start whether or not you're gonna succeed, right? So it's always possible that you start with a mini research project, and if during this phase you find out, okay, I was too ambitious and I don't have time or whatever, and you can again switch to read and report. And in read and report, or you can start with read and report, choose read and report to start with. And in this case, no team collaboration is allowed. Well, we say no ChatGPT, but you may use it with phrasing or polishing or checking your grammar. I mean, there's no way to stop you to do that. But if we find some of the read and report are quite nice and are quite interesting, we may invite you to give us more insight about those articles you studied, right? So in which case, we expect you to provide similar insight as demonstrated in your read and report submission. The detailed guidelines have been posted on Canvas. And if you wish to consult with us about your ideas, please send us a write-up of 1 to 2 pages by email with the email address listed in the beginning of the slides. And in case that we find or you think there are a little bit more to discuss, or it's not sufficient to have a 1 to 2 page write-up, we may schedule a meeting if needed. And a 1-page proposal is expected by the end of spring break. So if you are doing mini research project, think about how to formulate a research question and what could be a sensible choice to address this question. And for those who select read and report, you may write in your proposal what are the articles you plan to study and how they are connected with course material. So in the next lecture, we will cover deterministic rollout and its variants, as well as rollout for stochastic problems. As we announced, made in the announcement, given that the third homework is kind of stepping up from the previous one, we give 1 week additional time for you to complete it. And at the same time, please think about your term paper. And for those of you who are PhD student, we highly encourage you to try to connect what we have covered in the course with the research you are doing in your lab. So watch video lecture 5 from the previous offering in 23 offering of the course, and see you next week.